This is a video tutorial to accompany an article by myself and Mike Ronis, published in the Annual Review of Earth and Planetary Sciences in 2022. The topic is Pleistocene periglacial processes and landforms in the mid-Atlantic region of the eastern United States. Periglacial processes are those associated with cold climate, non-glacial conditions, and ground freezing. Modern analogs give good examples of the types of landforms and processes that accompany periglacial conditions, as here in Axel Heidelberg Island in Nunavut in Canada. This is a photograph from Sean Chartrand. And the dominant landform in this landscape is thermal contraction polygons. They are ubiquitous. They are on the benches, the side slopes, and the valley bottom, on the plateau highlands. They're the result of thermal contraction cracking, which occurs in very cold conditions and is diagnostic of permafrost, the existence of permafrost or permanently frozen ground. Another common landform in periglacial regions with permafrost is slumping and a variety of other types of mass movement. What can be seen here in the center near bottom of the view is an arcuate slump feature known as a retrogressive thaw slump. And as slumping occurs along the walls, as a thermokarst-like process with warming and permafrost thaw, there is slumping, and then that slumping exposes the base of the active layer, which is the top of the permafrost table. And that then is exposed and is warmed and thaws more, leading to more slumping, and the slumping then spreads laterally in all directions. That thawed, slumped area then becomes gullied and dissected, and the material removed from that, the material eroded, the sediment eroded from that, can accumulate down slope in fan-like landforms. So this is something commonly observed in periglacial regions today, and we can look for evidence of features like that in formerly periglacial landscapes, such as the mid-Atlantic region of the United States. And in fact, if we find thermal contraction polygons, then we can conclude that permafrost once existed in that landscape. On the right, again, Axel Heidelberg Island in Canada, at about 79 degrees north latitude. Thermal contraction polygons are ubiquitous on the upper slopes, side slopes, valley bottom. Note there's no through flowing stream. There is a low area, but it's frozen most of the year. It has permafrost, so there's not the typical kind of fluvial system we would see in a non-periglacial region that did not have permafrost. The same sort of landscape can be seen on the left in this Google Earth Air photo, a black and white version of it. This is actually in southeastern Pennsylvania in a shale bedrock environment. It's an Ordovician shale. And if you look closely, you can see traces of thermal contraction polygons. These are 18,000 years old and older. And the traces show up because the cracks, the polygonal boundaries, the cracked boundaries, contain sand and silty sand which had blown in at the time of cracking and opening of the ground as it contracted. The polygons in this case follow bedrock fractures, as do the ravines and side slopes, and most of this, the swale-like nature of the landscape follows the actual boundaries of polygons, which in turn follow the boundaries of fractures. So again, it's a landscape that doesn't have typical fluvial features and can be attributed to periglacial processes. Another landform very common in periglacial regions is mass movement that leads to lobes and benches. The process is known as solifluction. It's downslope mass transport of material produced by frost cracking and frost shattering. You don't see it here in this satellite view. It's not an ortho image. It's not obvious that there is a lot of colluvium on the landscape, but there's a hint of it To the right of the zigzag road in the center of the image, that's a boulder field on the slope, and that boulder field itself is a result of frost cracking and frost segregation ice processes, all of which are talked about in the paper. So boulder fields are mentioned several times in the paper, and what is known about them at present is described thoroughly. But the solifluction features don't show up as well in an image like this. But now if we look at a slope shade from a 1 meter LiDAR digital elevation model, you can see that on this hill and on the slopes of the hill, which is known as Chestnut Ridge in eastern Pennsylvania, there are widespread features that give the appearance almost of icing melted on a cake. And these are in fact the solifluction lobes and benches. Downslope, the lobes generally merge and produce wider benches. Near the upper parts of the slopes, the solifluction lobes are smaller. That's a phenomenon observed worldwide where solifluction lobes occur, as in Svalbard, Norway. We'll go back one more time. So note the road coming up the hill from the lower left to center. That's a new road built in 2019 to 2020 for an AT&T cell phone tower at the top of that hill. You can see that same road there here on this LiDAR DEM slope shade. But then notice how the lobes and benches themselves cannot be discerned in the imagery because the landscape is tree covered. Here's a modern example from Alaska in Ella showing active solifluction lobes and benches, and a variety of other features that represent mass movement. So solifluction is a mass movement process. It's a flow of sediment, matrix-supported sediment downslope. In many cases, it's associated with thaw of the active layer within the permafrost zone, and that active layer, as it thaws, moves across the still frozen substrate. In the lower right, you can see in the valley down below that colluvium is actually moving from the slopes down into the valley and filling the lower order streams. And that's what happened in much of the landscape in the mid-Atlantic region as well. Colluvium filled valleys, and colluvium came from the side slopes. And then throughout the Holocene, post-Pleistocene warming throughout the Holocene, streams have then begun to flow across that formerly colluvial landscape, and the substrate for many streams in the region is actually colluvium formed by solifluction. So what we've done for the readers of this article is shared imagery so that the reader can actually look at some of these landscapes that we're talking about in the paper and explore them through a series of images we put together in Mapbox. What we've done is created, where everywhere that you see red in this diagram, this is figure 9 from the paper, everywhere that it's red, we have provided LiDAR-derived imagery on Mapbox. Everywhere that's black, there is Paleozoic shale bedrock, which commonly has thermal contraction polygons, TCPs. And note in the legend that thermal contraction polygons mapped by George Gow in 2014 are shown in gray, and those that we are mapping are shown as white polygons. We are mapping those in the Paleozoic shale bedrock. Also, many workers have found frost wedges along the boundaries of thermal contraction polygons. Sometimes they only found the frost wedge and were not able to find the superficial trace of the relict polygon. But in quarries and road cuts, some previous workers have found frost wedges. Krantz, who did a PhD at Penn State, found quite a few in various soil pits that he dug and in quarries in central Pennsylvania, and those are shown as gray triangles. Several have been mapped and studied and dated and worked on in detail by Mark Dimitrov and his collaborators in the coastal plain. Those are shown in white triangles, and they're in table 3. And then also shown here are some orange triangles, which are areas of shale chip colluvium. In the places where we find the thermal contraction polygons in shale, we often also commonly find shale chip colluvium, and both are the result of cracking of rock. So shale becomes brecciated during segregation ice and frost cracking, frost weathering processes, and that chippy shale then can move down slope to make aprons of debris. So it probably moves during some form of solifluction. But it's such fine-grained material, it doesn't make prominent lobes or benches, whereas the sandstone from the sandstone hills does. So, starting at the upper right, there's a yellow line that is the last glacial maximum ice margin. We are going to move south from that and look at this red area here near Nisquehoning in northern Pennsylvania, then move south to Blue Mountain, and then north and west to central Pennsylvania, the State College area. And we'll be using the Mapbox material that we put together for you. We'll start with Nisquehoning. So what one sees initially when going to the Mapbox material we've put together is this image, which has a hillshade, a terrain view, a terrain rendering, surficial data, which in this case is geologic mapping by Dwayne Braun. Dwayne has mapped dozens and dozens of quadrangles in Pennsylvania. And then a site, which is a colluvium site of Dwayne Braun. So let's zoom in to the northwestern portion of this area and look at the hillshade. There's a quarry, there's actually a coal mine there. We'll come out a little bit south of there. We'll head in right about here. Turn on the terrain view, take a look at that, and note you can see with the hillshade view first, so there's the hillshade view on top, you can see some solifluction lobes. If we click anywhere within this polygon, we see that it's QSSC. QSSC, one of Dwayne Braun's mapping units, is Quaternary Stony Colluvium, derived from gray sandstone. It's matrix supported, supporting the interpretation of it being a solifluction derived feature. It has clasts that are slope parallel. That's also consistent with material that moves down slope via solifluction. The clasts are up to almost half a meter long, and they cover more than 25% of the ground, etc. The colluvium, as mapped by Dwayne Braun, fills small valleys and headwater areas of tributaries, and it occurs dominantly as coalescing lobes along the toes of slope. Continuing down to here, we can see there's QSRC, a similar unit, but it has it's a clast-rich diamix of residual and colluvial material derived from sandstone and shale. And as with the previous unit, the depth to bedrock is usually only a few meters. Now we're going to turn off the hillshade and look just at the terrain view. The terrain view is a composite rendering from a hillshade, a slope shade, and a map of local flow divergence. And that allows us then to see slope transitions more readily. It also makes high-frequency, low-relief surface textures more easy to visualize. So we can really clearly see now this much rougher surface from this bouldery colluvium. We can see more readily how much rougher the surface is from, as a result of that bouldery colluvium. We can tilt the landscape by using, I'm using Control and my mouse and spin it around and look off in the distance, zoom in and about, up close, far away, look at the various colluvial features, their ubiquity, their distribution, etc. Now we're going to go look at Blue Mountain to the south. So it's farther from the ice margin, the last glacial maximum ice margin. We have a terrain view here, and all the red dots are the sites of thermal contraction polygons that we have mapped. There is a frost wedge associated with one of these polygons that we have described in the paper and in another publication to come on this in this area. And this is Blue Mountain along the north. We're going to zoom in first to Blue Mountain. It's a prominent ridge along the southeasternmost part of the Appalachian Mountains that extends from northern Pennsylvania down over to southwestern Pennsylvania and on southward, in fact. We're going to zoom in closely. It's a sandstone ridge mapped in some places as quartzite. Here it's the Tuscarora sandstone. And notice then coming off of that ridge, the Tuscarora Ridge, coming down off that slope, we can see all the solifluction features in the colluvium, a colluvial apron coming out over the shale hills. And in fact, the sandstone colluvium derived from the ridge crest spreads out and over the shale benches to about here. It can be mapped out to about there. The contact of the shale is actually much farther up the slope, the shale sandstone contact. There's another sandstone unit in between the Tuscarora and the shale here, the Juniata sandstone. But sandstone from the ridge crest and from the mid-slope is actually mixed in with shale and carried far down onto the toe slope environment. We can again spin this and look along the mountain slope at that apron of debris that extends far across that colluvial toe slope environment and out into the shale, out into the dissected shale. The thermal attraction polygons do not show up clearly in LiDAR-derived imagery. They're very low relief features, and in fact, what makes them readily apparent in the aerial imagery, such as the Google Earth imagery that I showed, is that there's a contrast in moisture between the silty sand in the cracks that form the polygon boundaries and the drier fractured shale bedrock. So at certain times of the year, the polygons show up very clearly. We don't see them here even with this terrain rendering. They're just too low relief. If we were looking at Google Earth imagery, they'd be very obvious. And then lastly, we'll go to State College in central Pennsylvania. Again, we have a hillshade, terrain rendering that's a composite of the hillshade, slope shade, and map of local flow divergence. But we've also added some soil map units. We've bundled together all the soil map units that are described by the U.S. Department of Agriculture as residual soils. Those are in pink. And all of those that are described as colluvial soils, those are in green. And then all those in blue are the soils that are mapped as rubble. So if we come along Tussey Mountain, for example, which is right here, another sandstone ridge within the Appalachian Ridge and Valley, and we'll turn off the soil units for a moment, and then we'll tilt the landscape. One can see that there's a tremendous amount of colluvium that has moved down slope from the sandstone ridges and has solifluction features. And in this case right here, it's filling this low valley. This is a region dominated by anticlines, plunging anticlines and synclines, hence this very remarkable looking landscape of accordion-like folded ridges and valleys. But solifluction is dominant all along this slope and that slope. Now we'll turn on the terrain view and turn off the hill shade, and one can see even more of the details of this remarkable landscape forming process. A periglacial process from formerly more cold times when cold conditions prevailed, in contrast to the landscape today, which is was heavily vegetated with trees. So if we now add in the soils, you can see that all the areas with clear solifluction features are mapped as colluvial soils. It's a variety of types of colluvial soils, such as the Andover soil series. And then the red areas are mapped as residual soils on the mid-slope, and then farther upslope are blue rubble areas. So those are the sandstone ridge crests where there are cracked and shattered boulders, but they're mapped as rubble because the rubble has not clearly moved down slope as it has down below. A number of other sites are shown over here. These are described at length in the paper, so you can look at them there. But they include the work of Jo Marie Del Vecchio with her advisor and collaborators, her advisor Roman DiBiase at Penn State, and there are many other collaborators. All right, well, enjoy the Mapbox material we've put together for you in conjunction with the paper on periglacial processes and landforms in central Pennsylvania. Thank you.